Module 6, Lesson 2, Sampling Distributions. Suppose we have a random sample of size n from a population, and we typically think of the population following some theoretical distribution. Well, we can calculate a sample mean. We can calculate the sample variance. Now, some remarks. First of all, these are point estimates for, well, the theoretical mean, mu, and similarly the theoretical or population variance, sigma squared. Okay, my next remark is that the sample mean and sample variance, well, they change from one sample to the other. Given a sample, well, you may not get the same sample mean as the last sample that you got from this population. And the last remark, this random sample, x1 through xn, really, this x1, x2 through xn are independent and identically distributed random variables. And so the sample mean and sample variance, these, first of all, these are functions of this capital X1 to capital Xn, and hence the sample mean and sample variance are random variables. I have underlined this part, sample mean and sample variance are random variables. This is the important part of this remark. Now, for any point estimator, could be mean, could be variance, could be some other statistic, the probability distribution of this. So thinking about this point estimator as a function of x1 through xn, hence a random variable, well, this changes with sample size, and this is called the sampling distribution. Now, in this video, we will discuss the sampling distribution of the sample mean and the sampling distribution of the sample variance. So let's begin with the sampling distribution of the sample mean. In fact, this we already know some things about, but I can just remind you. Recall, if you have x1 through xn, a random sample from a distribution, mean mu, variance sigma squared, well, then this random variable, which is our sample mean, it's a linear combination of x1 through xn, and we discussed, back when we were discussing central limit theorem, it has mean, mu, and the variance was sigma squared over n. To get this, we just use properties of linear combination. Well, when you have independent random variables, we needed that for this one. Well, that's very nice. We know the sample mean. Its mean is mu. Its variance is sigma squared over n. But the question is, what is the sampling distribution of the sample mean? So what distribution does this random variable follow? Well, let's start off with x1 through xn, a random sample from the normal distribution. Mean mu, standard deviation sigma. Okay, so then the sample mean, well, it's a linear combination of normal random variables, and so it itself is normal, and it's distributed as normal, where the mean is mu, and the standard deviation, well, we take the square root of the variance, so we get sigma divided by the square root of n. Now, have we seen this before? Well, yes. This should remind you of central limit theorem. In fact, I'm going to use that in just a moment. So the good news is, my first remark is that for large n, maybe I should highlight this part, put a little arrow. So for large n, say we have finite mean and variance, the central limit theorem applies. What did the central limit theorem say? It says exactly the same thing. Really, it says that the sampling distribution of the sample mean is approximately normal. And we talked about this, really, we talked about this in the last module. Okay, now I'm going to rewrite the above. So let's stare at this. It says that this is a normal random variable, and there's a transformation for a normal random variable to get to a standard normal random variable. How do we do this? Well, we take x bar minus the mean, divide by the standard deviation. And here the standard deviation is sigma over the square root of n. This will be distributed as n of 0, 1. This is our standard transformation from a normal random variable to a z, or standard normal random variable. Okay, definition. Well, this quantity that we see, sigma over square root of n, which is the standard deviation of the sample mean, well, it has this name. It's called standard error of the sample mean. Now, in practice, we do not generally know the population standard deviation or theoretical standard deviation sigma. And so this, the standard error of the sample mean, we don't have it exactly. Okay, well, how could we estimate it? Well, we have this random sample, x1 through xn. We have its mean. We add up, k equals 1 to n, xk, and then divide by n. And we have this sample, standard deviation. Well, the best estimate of the standard error of the mean that you could get from your sample would just be this. We take the sample standard deviation divided by the square root of n. This is the estimated standard error of the sample mean. It comes directly from your sample. Now, notice, once you have n and you have your population, this is just a fixed number. Your sample can vary. This stays the same. Sigma over square root of n. However, this is not a fixed number. As your sample changes from one sample of size n to the next, this will be a different value because your standard deviation will change. It's based on the sample. So the question is, how is this distributed? Okay, we take x minus the mu over this estimated standard error of the sample mean. We should not expect it to be a normal random variable. Well, to answer this, let's start off with a random sample from a normal distribution. Mean mu, standard deviation sigma. And we can ask, how is this statistic distributed? Well, x bar minus the mean over this s over square root of n. Okay, I expect this to have mean 0, but because now this is not a fixed number for every sample, it varies with the sample, I would expect this distribution to have a bit more variance, larger variance than the standard normal. That would say larger variance than 1. And I will tell you, this follows a t-distribution with n minus 1 degrees of freedom. Now the good news is, okay, what did we see here? For large n, central limit theorem applied, and we had that the sampling distribution of the sample mean was normal with mean mu, standard deviation sigma over the square root of n. Okay, here, same thing. So for large n, even if the normality assumption, so even if x1 through xn does not come from a normal distribution, well, we will still approximately have the above result due to the central limit theorem. This is fantastic news. Now, you might be wondering, what is the t-distribution? Is a distribution I did not talk about a few modules ago. Well, first of all, it's a continuous distribution. We have used it a few times in some examples in our Canvas pages, but I will talk a little bit further about it right now. This distribution has one parameter, which you could call maybe k, and this is the degrees of freedom. And k needs to be some positive number. Typically, k will be a positive integer, 3, 4, 5, 6, something like this, but really it's defined for any positive k. Now, the mean of this distribution is 0, provided k is bigger than 1. And the variance of this distribution is k divided by k minus 2 if k is bigger than 2. So you notice same mean as the standard normal, it's 0, but the variance, it's bigger than 1. And I have a few plots here. So what we're looking at, I'll write this above, are probability density functions plotted. And in each one, I have one t distribution and I compare it to the standard normal. So this first one, we have 2 degrees of freedom, 5 degrees of freedom, 10, and 20. Now, it is the case that if you let the degrees of freedom go to infinity, so grow without bound, the t distribution will approach the standard normal, but it is a different distribution. All right, so what I'd like to do now is I'm going to switch to R, and we're going to look at a Monte Carlo simulation for one example to see that this makes sense. What I'm going to do in R is I'm going to sample, so my n will be 10. Let me do one example of what I will do, and then we will go into a loop. So what I've done is I have sampled 10 from the normal distribution. I've chosen mean 2. I've chosen standard deviation 3. And then what I will do is create this t-score. Take the mean of this random sample minus 2, which is the population mean, divide by the standard deviation of this random sample over the square root of 10. And you see this one value, we have 1.702658. Now, this is one value of a t. What I'd like to illustrate is if I have many values of this statistic, that it follows a t distribution, it should be 9 degrees of freedom. Okay, so now I'm going to create this. This will be a vector, capital S, capital T. We are going to sample 100,000 times. We'll have 100,000 really observations of this statistic. And now let's create a for loop to do that. All right. We can make a histogram. So here is a histogram of this sample. On top of it, I have overlaid the probability density function for the t distribution with 9 degrees of freedom. Now, we know that histograms are not the best way to compare a distribution with a sample. So let's look at a QQ plot. This is a QQ plot comparing my sample, which was capital S, capital T, with the distribution, well, the t distribution with 9 degrees of freedom. And you see this looks really good. So this is an illustration of what we just discussed. Welcome back to my iPad. Now, the next thing we want to discuss is the sampling distribution of the sample variance. So we have a random sample, we have the sample mean, and we can certainly calculate the sample variance. The question is, how is this distributed? Well, we have a theorem, x1 through xn, a random sample from the normal distribution, mean mu, standard deviation sigma. Okay, then we have this s squared. Here's the sample variance. We have n minus 1 times s squared over sigma squared. This part though, so n is fixed. It's the size of our random sample. Sigma is a number. It's the standard deviation of this normal distribution. So this whole part, n-1 divided by sigma squared, is some number. So what this is saying is this multiple of the sample variance follows, well, it follows a chi-square distribution with n-1 degrees of freedom. Chi-square we talked about in our common continuous distributions video. It's a special case of the gamma distribution. But this is the statement. Now, unlike the previous page, where we can use central limit theorem, here, this requires x1 through xn to be normally distributed. And I'm going to illustrate that in just a moment. So what I'm going to do, we're going to switch back to R. We're going to run two different Monte Carlo simulations. For each, we will take 100,000 samples. The sample size is 10. But on the one hand, I will take 100,000 samples of size 10 from the normal distribution, mean 1, standard deviation 1, and then 100,000 samples of size 10 from the exponential distribution with parameter 1. Now, both of these have variance 1, and so this quantity, n-1 is 9. This quantity is 9s squared, and so I will be comparing 9s squared to the chi-square distribution with 9 degrees of freedom in both cases. We should see it looks great for this one, and we should see here there will be a problem. I have cleared any saved objects. Let's see, which one do we want to do first? Maybe let's do the one that will look great first. So first, I am creating a sample of size 10 from the normal distribution with mean 1 and standard deviation 1. Okay, then I do that 100,000 times. But for each sample, you see I'm recording 9 times the variance of the sample. So this is 9s squared, that statistic. All right, so I have this now in a vector called S var. We can make a histogram. Oh, you see how wonderful this looks? This is a histogram with the probability density function of the chi-square distribution with 9 degrees of freedom overlaid. But as we know, QQ plots are really a better way to see things. So let's make a QQ plot for this example. Maybe I should save this first. And I will add it to the PDF notes that I post for you in Canvas. Okay, now we can run this QQ plot. This is comparing 9s squared, where we sampled from the normal distribution, to the chi-square distribution with 9 degrees of freedom. Whoa, this looks very nice. So far, we have one example to illustrate our theorem about the sampling distribution of the sample variance. Well, I mentioned it required normality. So I'm going to do the exact same thing as I mentioned I would using the exponential distribution. So I sampled from the exponential distribution 100,000 times, but each sample is of size 10, and my rate parameter is 1. And then I stored 9 times the variance of, well, each sample. We can make a histogram. This is hard to see, but at least so far, it doesn't look nearly as nice as when we sample from a normal distribution. So what would be a more accurate representation of comparing the distribution, chi-square with 9 degrees of freedom, to the sample, as we know, QQ plot. So let's do this. Okay, you can see, even if you ignore the blue line, If you just look at the points, these points do not fall on a line, and so it does not look good. This statistic, 9s squared, definitely does not look like it follows a chi-square distribution with 9 degrees of freedom. All right, well, I have included the pictures we just created in R. Here was for A. I can draw a line. And here is from B. So here the x1, x2 to xn from the normal distribution with mean 1, standard deviation 1, and then down below, letter B, x1 through xn came from the exponential distribution with lambda equals 1. And well, I like this example because it illustrates this discussion we had about the sampling distribution of the sample variance. Thank you so much, class, and I will see you in the next lesson.